Have you ever wondered how Spotify just knows the perfect song to play next? Or how Amazon can sift through millions of products to find the exact one you're looking for? Well, it all comes down to this hidden language, a secret code that brings order to all that chaos. And today, we're going to decode that language, starting from the ground up.
So, let's just kick things off with a big question. I mean, we live in a world that is just overflowing with data, right? It's messy, it's disorganized. So how in the world do computers take all of that digital noise and turn it into perfect, searchable, and reliable order?
You know, the answer is actually way simpler than you might think. It all begins with a concept you already get, the idea of a collection. In math and computer science, this has a special name. We call it a set. And believe me, it is the fundamental building block for organizing pretty much everything, from your phone's contact list to the entire internet.
Okay, let's dive right in. Our first and maybe most important building block is this thing called a set. So, a set is really just a group of things, but it has to follow two super important rules. First, every single item in the set has to be unique, no duplicates, none. And second, the set needs to be well-defined. That just means it has to be crystal clear what's in and what's out. For example, the set of all tall people isn't great, right? Because tall means different things to different people. But the set of all people over 6 feet tall, that's perfect. It's a clear, measurable rule. Now, this is probably the most straightforward way you'll see a set. You just list everything that's in it between these little curly braces. This is called the roster form, and it's perfect when you've got a small, easy-to-manage group of items. But what if you have a set with millions of things? Like, say, all the users on Instagram. You can't possibly list them all out, and that's where Set Builder form becomes a lifesaver. Instead of listing every item, you just state the rule that all the items follow. It's like a membership rule for a club. You just say, the set of all Instagram users, and that simple rule defines that absolutely massive collection. So we've got our basic building blocks. Awesome. Now let's see what we can actually do with them. Let's start combining and comparing different sets. First up, we have the subset. And honestly, it's pretty much exactly what it sounds like. It's a set that's tucked completely inside another bigger set. Think of it this way. The set of all your friends on Facebook is a subset of all Facebook users. Every single one of your friends is a Facebook user, right? But not every Facebook user is your friend. See? Simple. And this is where things get really cool, and you start to see the power we're unlocking. A tiny little set with just 3 items in it can be broken down and organized into 8 different unique subcollections. That includes the empty set with nothing in it and the whole set itself. This ability to create subsets is what makes things like categorization possible. Okay, next is union. Think of this as the ultimate merge button. You're basically taking 2 collections, dumping them into one giant bin, and keeping absolutely everything. If an item is in set A, or if it's in set B, or if it's in both, it makes it into the union. Let's look at this example right here. We're combining all the numbers from both sets. But wait a second. Notice the number 2? It's in set A and in set C, but in our final union, it only shows up once. Why is that? Well, remember that first rule of sets we talked about? All items have to be distinct. The union automatically gets rid of duplicates for us. Now, if union is all about merging, intersection is all about finding the overlap. It's the search for what 2 different groups have in common. An item only gets into the intersection if it exists in set A and it exists in set B. So here's the crucial thing about intersection. It lets us be incredibly specific. It pinpoints exactly what's shared between these 2 different groups. This is how a database could find, for example, all the customers who both bought a product and also left a 5-star review. All right, so we can group things into sets, and we can compare those sets. But how do we build a bridge between them? How do we formally connect an item from one set to an item in another? This is where something called the ordered pair becomes absolutely essential. It's just a simple little package of 2 items, but it has one critical rule. The sequence is everything. The pair AB is totally different from the pair BA. It's just like coordinates on a map, right? The point XY is not the same as the point YX. So what if we wanted to map out every single possible connection between 2 sets? Well, that's what the Cartesian product is for. Imagine you have a set of t-shirt sizes, small, medium, large, and a set of colors, red, blue, green. The Cartesian product would give you every single combination: small red, medium red, large red, small blue, and so on. It's the whole shebang. You can see exactly how it works here. It's really systematic. We take the 1 from set A and pair it up with everything in set B. Then we take the 2 from set A and do the exact same thing. The result is this complete map of every possible link between the two sets.
And this is the big aha moment. This quote tells us that a relation isn't some new complicated thing we have to learn. No way. It is simply any group of ordered pairs that you decide to pick out from that giant Cartesian product we just made. A relation is just a specific set of connections that you actually care about. Okay, it's time for the final piece of the puzzle, the big payoff. We've gone from simple collections to making specific connections. Now it's time to build a powerful, predictable rule-making machine. So we know that a relation is just a set of connections, but why are some of them so much more useful and powerful than others? Well, it all comes down to one critical, very special rule. This is the golden rule of functions, okay? For every single input, you are guaranteed to get one and only one output. No maybes, no multiple answers. It's this absolute reliability, this predictability, that makes functions the absolute workhorses of all of mathematics and all of programming.
Let's make this crystal clear. Look at the example on the left. Each input, 1, 2, and 3, has exactly one partner. It follows the rule. Perfect. Now look at the right. Uh-oh. The input 1 is trying to be paired with 2 different outputs, 2 and 3. That breaks the golden rule. It's still a perfectly fine relation, for sure, but it is not a function.
So let's just do a quick recap of the journey we just took. We started with the simple idea of grouping things into sets. Then we learned how to combine and compare them with operations like union and intersection. After that, we built bridges between them using relations. And finally, we created these powerful, predictable rules called functions. From the way your social media feed is built to how your bank account works, this fundamental language of organization is, I promise you, absolutely everywhere. And why this all matters is that you now have the key. You have the concepts to see and understand the logical blueprint that holds up our entire digital world.